Issue with inverse and regular Laplace transforms is that there are way too many of them to memorize. For example, we have the Laplace transform of e to the at, that's 1 over s minus a. Wouldn't it better to derive it instead of always using this bulky formula, or just needing to memorize like a page of them, of these dumb Laplace transforms? Because we can use them to simplify regular differential equations by converting them to algebraic expressions. And there's actually a way to do that with Euler's formula, this thing right over here, which we keep on seeing, and that's for a reason. Because in calculus 2, it's everywhere. It's just everywhere. It's so versatile. So an instance of another application of this formula is for deriving the Laplace transform of sine at and cosine at with these that I just spent a minute talking about. But how can we actually derive it with e to the at? Well, directly substituting in the form. That's the pound sign. Oh my god, you just rub that out. I can never get these right. Okay. But consider the Laplace transform e to the xt. What I just did was substitute a with ix, which converts this to a 1 over s minus ix. You see, I just substituted in a with ix. Now I don't really know what to do to simplify this other than multiply this by the conjugate. Because I want this in a form where I can take a real and imaginary part. I want to take the real and imaginary part of whatever I get, right? So by multiplying by the conjugate, I'm gonna get, I wrote IA, that's wrong. I always use FOIL because I can't do anything else. I probably should memorize some stuff, but okay, s times s, we get s squared. S times ix, that leaves us with six, negative ix, times s, but negative s times ix. But we see these cancel out, so that's what we're going to do. Now we do ix times negative ix. That'll give us positive x squared, because I times I, negative 1. Negative 1 times negative 1, positive 1, times x squared, because we multiply two x terms. So now that leaves us with s plus ia over s squared. Wait, you can't see that. S squared plus x squared. S squared plus x squared. Now, remember, I want to take the real and imaginary part. How can I do this with what I have over here? What I'm going to need to do is split the fraction. Split the fraction. Like this. I'm going to do s over s squared plus, never mind, x squared. My s and x sound similar because I think I have a list or something. It doesn't really matter. Now, that's going to do s over s squared plus x squared plus I times a over s squared plus x squared. Because remember, we want to isolate a term that contains the imaginary unit to find the imaginary part of our Laplace transform over here to get these. Mind the laundry basket. Okay, so when we do this, I don't need to patronize you, it's kind of easy. The real part of the Laplace transform of e to the a, keep messing up. It looks so ugly too. E to the at, boom, will just be whatever term in this that does not, you can see my trousers, that does not contain the imaginary unit. That's just s over s squared plus x squared. Over s squared plus x squared. Yeah, sorry. And now the imaginary part of blah 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 blah, can't be asked to write it again, will just be whatever term does contain I, which is just a over here, a over s squared plus x squared. That's pretty good, right? We got our answers. Boom, boom, boom. But we just